All right, hello and welcome. In this example, we're going to look at how to calculate total inductance in this series circuit here. And we're going to then measure our total impedance for that circuit and recalculate our total inductance from that measurement to verify if the measurement's accurate. Okay, so the first thing we need to do is sum up our series components here. Since these are inductors and they're in series, we can just add them all together. We'll look at each one of those inductors and they're in millihenries, each one of them. And so we can just ignore the millihenries for now and leave it till the end. So we'll say 1 plus 20 millihenries plus 3 millihenries plus 15 millihenries gives us 39 millihenries. So write that down here as our total inductance is 39 millihenries, right? And that will be LT, right? And now we're going to measure our XL. That's our impedance for the circuit, XL. Right, and that we know is going to be an ohmic value, right? It's the resistance of our inductors. And we're going to call that resistance inductive reactance instead of resistance. But it's equivalent to the same thing, and it's why we can use Ohm's law. So the next stage, we have to find our impedance meter. And there's two locations for that. You can find it here in the sidebar here. If on that bottom, you have a drop down next to this lab view symbol. And the second button on that drop down is your impedance meter. You can pull that out. Looks like that. The other option is in your Simulate tab. You can go to your Instruments, down to LabVIEW Instruments, and then pull out your impedance meter from there. They are the same component. They're just two locations that you can find them at. So this is going to be treated a lot like measuring resistance in a circuit. We can't have a voltage source attached to it, and we want to wrap the positive terminal to the front of our circuit and the back terminal to the back of our circuit. And this meter is actually going to induce a frequency through our inductors so that we can measure our impedance. Right? If we don't induce a frequency, we cannot measure these inductors in terms of impedance. And so when we double click on our impedance meter, we're given a new window. And that's here. And so we see that the frequency sweep over here is going to allow us to range our frequency. We have a start and a stop frequency. So if you have like a low pass or high pass or band pass filter using inductors, capacitors, resistors, then you're going to want to sweep your frequency range. You're going to want to start at like 1 hertz, go all the way up to like 10,000 hertz and see where your filter's filtering out. Right? And so that can be a way to do that, a way to test your filter range. And you can do a number of outputs also. So if you wanted to scale it differently, there's a lot of options for that. But we're really just going to use it as the most simplest form. It's just going to measure our impedance. So it's going to induce a 60 hertz frequency. That's our start and stop frequency. And then it's going to tell us the resistance in the circuit, the inductance in the circuit, and the total reactance of the circuit. So when we hit play on this, we'll fill in that top line. Stop that again. This means that we have 60 hertz. That's what we tested our circuit on. So when we calculate, we need to use 60 hertz. And this over here says that the resistance, the linear resistance, like resistors in the circuit, is 1.2 times 10 to the negative 8. It's really, really small, which means there is no linear resistance, right? And we see that up here. There is no resistors in this circuit, which means that this should be pretty much 0. This X value here is going to be our XL, 14.7. And that's going to be in this box pretty much every time. If you're looking for inductors, look for the X box. But if you have capacitors and inductors and resistors, you need to read the Z box here. Right? As soon as you get into capacitors, that starts to be really important. So make sure you're looking at both of these too. And if you're looking for inductors, you can use the X. And if you're looking for capacitive reactance, you can use the Z. Okay, so one more thing about this meter here is it gives us the equations we need in this little question mark box. We can click on that, and that gives us a new pop-up window that tells us about capacitive reactance, inductive reactance, net reactance, and total impedance. And it kind of gives us that rectangular polar form conversion also, right? Because this is rectangular form, and then we can convert to polar form. So we want to use XL because we just found XL, and we can calculate our L out of that, right? Because XL equals 2 pi FL. 2 pi is our circle rotation. That's a full rotation of a circle. F is how fast we're moving around that circle, and L is the impact of our inductance. And so we want to solve for L out of that equation. So that's what we're going to do. So we'll take our 14.7 and use that as our XL value. 14.7 ohms, right? It's now in ohms. These two mean the same thing. They're both talking about this 4 group of inductors here. So next we're going to calculate our total inductance. It's going to be LT, right? That's what we want to solve for, but we have XL. And so let's rearrange that and say that, let's write out our XL equation first, I guess. We'll say XL is equal to 2 pi. That's our circle. F, the speed around the circle, and L, T. That's what we're aiming at, right? Our total inductance. And so it should match our original total inductance of 39 millihenries. So we can plug this in. We can say that we know what XL is. It's 14 14.7, and that equals 2 pi. We know what our frequency is. Our meter put it in there, right? 60 hertz. And then we'll multiply that by our LT, which we don't actually know yet. We do know, but we're going to solve for it here and verify that it matches. So to do this, we want to reduce this out so that LT is on one side. So we can divide by 2 pi times 60 to both sides. And that's going to give us our final answer, right? LT is equal to 14.7 divided by 2 pi times 60. Right, and when we plug that in over here, let's send that out. 14.7 divided by 2 pi times 60. And that gives us a small number. That's what we expected. So LT is equal to 0.0389. We can round that up because we know what it's supposed to be, right? So we'll say that this is actually equal to, I'll move it back 1, 2, 3 spots here to the -3. So that's a milli. We'll end up with 39 millihenries. All right, let us know if you have more questions on this part.